we're going to find the inverse Laplace transform of 4s squared plus 4s over s plus 2 times s squared plus 4. Once again, the first step here is partial fractions, to try to break this up into more manageable pieces. So, again, I'm kind of relying on you to remember the partial fractions from Calculus 2. Got a lecture on partial fractions in the Calculus 2 lectures here on Educator.com if you're still rusty on that. But remember, we want to set that equal, we want to set up our generic partial fractions expansion form, s plus 2 over s squared plus 4. And our generic, well, we try to factor the denominator, but we can't factor it any more than it's already been given to us. We got an s squared plus 4 in the denominator. That doesn't factor anymore. So we just got to write this as a over s plus 2. And then we have a term over s squared plus 4. And we're going to have to call that bx plus c. So our goal is to find the a, the b, and the c. That's the goal of partial fractions. And so we're going to multiply both sides by our common denominator in order to get rid of the denominators, s plus 2 times s squared plus 4. And so when we do that, on the left-hand side, we'll get 4s squared plus 4s. On the right-hand side, we'll get a times s squared plus 4 plus bx plus c. I wrote x. Of course, I was thinking in terms of calculus when we always use x as the variable, but in this case, it's an s. So b times s plus c. And we've got s plus 2. And now, essentially, we want to solve for a, b, and c. It's a little bit messy, but I see something quick that I can do and find out one of my coefficients right away. And that's if I plug in an s equals negative 2, that'll make all these terms drop out. So I'm going to go ahead and do that. S equals negative 2. And on the left side, 4s squared will be 16, because it's 4 times 4. Plus 4 times s is minus, since s is negative 2, minus 8, is equal to a times s squared is 4 times plus 4 is 8. And the whole point here is that the bs plus c terms get multiplied by 0, and therefore they drop out. And so we get a times 8 is equal to 8. And so right away we figure out that a is equal to 1. And that's kind of as far as we can take it in terms of cleverness. Now we have to actually expand out that expression on the right, and it's a little messy, but it's not too bad. 4s squared plus 4s. I've already figured out that my a is 1, so I'm going to go ahead and write s squared plus 4. Now I'm going to expand out this bs plus c times s plus 2. So that's bs squared plus 2bs plus cs plus 2c. And I'm going to sort that out into powers of s's. So I see I've got 1 plus b times s squared. That takes care of that term and that term. Now my s terms are going to be 2b plus c. 2b plus c is going to be my s terms. And my constant terms is going to be 4 plus 2c. This is still equal to 4s squared plus 4s. And so from my s squared terms, I see I'm going to get 4 is equal to 1 plus b. From my, I think I'm going to skip to the constant terms because that looks a little simpler. Constant terms tell me that on the left I have 0 as a constant. On the right I have 4 plus 2c. And so that's probably enough that I can solve for b and c. I won't worry about the s terms because I don't need it. But I see if 4 equals 1 plus b, then b is equal to 3. And if 4 plus 2c is equal to 0, then my c is equal to negative 2. So that means that I've figured out all my coefficients, a, b, and c. And so I can complete my partial fraction expansion, 4s squared plus 4s over s plus 2 times s squared plus 4 is equal to, it was a over s plus 2, that's reading up here, and my a was 1, so 1 over s plus 2, plus bs plus c, reading here. My b is 3, so 3s minus 2, c is negative 2, and I've got an s squared plus 4 here. So that's as far as I can go with the partial fractions, and now I want to look back at my Laplace transform chart and see if I can find any functions that generally match the terms that I've got here. And so I'll look at my Laplace transform chart. Remember, I posted that chart at the beginning of the lecture, so you can flip back a few slides and you can see the chart posted back there. And let's see what we have here. Something that matches these terms that we have. I see the Laplace transform of e to the at is 1 over s minus a. The Laplace transform I see for cosine of bt is s over s squared plus b squared. I picked that one because it looked like it might match the second term of our partial fraction expansion here. And the Laplace transform of sine of bt is equal to b over s squared plus b squared. And I'm just going to make a note here. I see I've got s squared plus 4, which means our b is going to be 2. So if b is equal to 2, then this would be equal to 2 over s squared plus 4. And our cosine of bt would be just s over s squared plus 4. So I think that's going to be enough to figure out my inverse Laplace transform. This last term here, I'm going to separate it out and write this as 3s over s squared plus 4 minus 2 over s squared plus 4. And now I think I can write down my inverse Laplace transform. F of t, I see 1 over s plus 2, and I figured out the Laplace transform of e to the at is 1 over s minus a. So I guess my a there would be negative 2. So this would be e to the negative 2t. Now I have 3s over s squared plus 4. So that's 3 cosine of bt. Well, b is 2, so cosine of 2t. Minus 2 over s squared plus 4. Well, 2 over s squared plus 4 is sine of bt, so minus sine of 2t. It's not 2 sine of 2t, because this 2 is, we don't want to think of it as a coefficient. That 2 becomes that 2 right there. So we don't have another 2 outside the sign. And that's it. We've got our inverse Laplace transform of the function that we started with. So let me go back over that quickly and remind you what each of the key steps there was. The first key step is remembering how to do partial fractions. So remembering what you learned in Calculus 2 about doing partial fractions. We want to expand this function out into its partial fraction expansion. So that's a over s plus 2. And then since we can't factor s squared plus 4, its expansion is just bs plus c. And then to figure out the a, b, and c, we want to clear denominators. So that's what I'm doing here, is multiplying both sides by the common denominator. That gives us on the right a times s squared plus 4, bs plus c times s plus 2. And I notice I'm really trying to solve for 3 variables, but I can get one of them quickly by plugging in an s equals negative 2. I noticed that by looking at that. If I plug in s equals negative 2, that term will drop out. So s equals negative 2 on the left gave us 16 minus 8. On the right, made this one term drop out, and it gave us a times 8. So quickly we figured out a is equal to 1. But then the other coefficients were more work. I took the a equals 1, I plugged it back in up here. So we got s squared plus 4, and then I expanded out bs plus c times s plus 2. So that's how I got all of these terms. And then I kind of sorted them out into terms with s squared, terms with s, and terms with the constant. And I equated like terms on both sides. So on the left, I first looked at s squared. On the left, I got a 4. That's that 4 right there. And on the right, I got 1 plus b. So that told me quickly b was 3. And then I kind of skipped over s because it looked a little more complicated. I skipped right to the constant. On the left, I got 0. That's kind of coming from that 0 there. On the right, I got 4 plus 2c. So that's where that came from. And that was an equation I could quickly solve for c being negative 2. So then I took that a, b, and c, I plugged them back into my original guess, a, b, and c, and that's how I figured out this partial fraction expansion. That's kind of the end of the Calculus 2 portion. But then I looked back at my Laplace transform chart, and the goal of that is to find some functions that match this expansion. So when I looked at my Laplace transform chart, I saw 1 over s minus a coming from e to the at, and I also saw s over s squared plus b squared coming from cosine of bt, and b over s squared plus b squared coming from sine of bt. So that looked pretty hopeful, and I noticed since I had a 4 here, I must be using b equals 2, because it's always s squared plus b squared. And so I figured out, all right, if I plug in b equals 2, for the sine I'll get 2 over s squared plus 4. For the cosine, I get s over s squared plus 4. And so in order to invoke those, I separated this out into the 3s part and the 2. The 3s part gave me 3 cosine of 2t. And the 2 gave me sine of 2t, not 2 sine of 2t, because there was already a built-in 2 here. So that 2, I used it to match that, and I didn't have another 2 left over as a coefficient. Meanwhile, this 1 over s plus 2, I see that I had a equals negative 2 here, so that just turns into e to the negative 2t. So I put all those parts together, and I get the original function of t, for which, if you took the Laplace transform, you would have gotten this function of s that we started out with. So what I really found here was the inverse Laplace transform of that function of s, and my answer is a function of t. So that's the end of this set of lectures on Laplace transforms and inverse Laplace transforms. In the next lecture here, we're going to see how we can use Laplace transforms to solve differential equations and solve initial value problems. So that's the next lecture in this series on differential equations here on Educator.com. My name is Will Murray. Thanks for watching.